Back in chapter 6, I showed you how to graph the sine and cosine functions, as well as the other trigonometric functions. And when we talked about the graph, we had, for example, something that looked like this for a sine function. We learned that this value here is called the amplitude. For an unshifted, untransformed sine graph, that amplitude is 1. But sometimes the amplitude can be more than 1. It can actually be less than 1 as well. We also talk about the period of a graph. The period of an untransformed sine function is 2 pi, but it can be more than that or less than that, depending on whether it's been stretched or compressed in the horizontal direction. Functions can also be shifted up or down. And we learned alongside all of this, the graph of a function, a sinusoidal function, will have an equation like this. A times the sine or the cosine of b times theta minus c plus d. And the a here represents the amplitude. The d represents how far up or down the graph has been shifted. The b represents how many copies of the graph you can get in between 0 and 2 pi. In the case of sine or cosine, between 0 and 2 pi. If it's only 1, then b would be 1. If you can squeeze 2 copies in, then b would be 2. And that tells us something about the period, but it doesn't tell us that that's what the period is. The period is not 2. The period is 2 pi divided up into b equal parts. The c is the horizontal shift. This graph has not been shifted horizontally. What we're going to talk about in this section is exactly this same stuff again, except that instead of giving you a graph and asking you for the equation, or giving you the equation and asking you for the graph, I'm going to give you a scenario, a situation, and I'm going to ask you to come up with the equation for that situation and possibly using a graph to get there. Your textbook makes the point of saying that sometimes instead of capital A, lowercase a is used. When I write trig here, I mean you could use sine or cosine. Technically, you could also use tangent, cosecant, secant, and so on. It also makes the point that in applications, often b is referred to as omega. And then we have theta or x or t plus or minus c plus d. Now, plus or minus is valid here. We can have a positive c or a negative c, but I would argue that minus c works just as well, because if c is a negative number, you're going to get theta plus that number, right? That said, your textbook feels like it's an important thing to point out that you can use omega instead of b, you can use lowercase a instead of capital A, and sometimes you see plus or minus here. These are conventions depending on the context or depending on the discipline in which you're working, the field in which you're working. You may also see other variables as well, but we'll just stick with these ones for now. In example 1 of your textbook, showing how the properties of a trigonometric function can transform a graph, we've already done all of this. If you look at this function, if you look at this example, they point out that the horizontal shift is pi over 8, I believe, because you have to factor out, it's not actually shown, you have to factor out that 4 from the parentheses. Here, I'll write it down in case you don't have your textbook in front of you. Y equals 2 times the sine of 4x minus pi over 2 plus 2. And I always start by rewriting these by factoring out the argument. Divide 4x by 4 and you get x. Divide pi over 2 by 4 and you get pi over 8. Now we know from our previous work that this graph is going to be the graph of sine, shifted pi over 8 units to the right. We're going to squeeze 4 copies of this graph between 0 and 2 pi. That's going to mean that the period of one segment is going to take pi over 2 units. So one repetition of sine, something that looks like this, instead of taking 2 pi, is only going to take pi over 2. That's a really pretty compressed graph of sine. So we're going to compress it so there are 4 copies in the 0 to 2 pi region. Then we're going to double all the y values, making it taller than having a height of 2 rather than a height of 1, like a standard graph would have. Then we're going to take the whole thing and shift it up 2 units. We've already talked about this, so there's really not a whole lot more we need to discuss in this subsection. Example 2 says finding the amplitude and period of a function. Well, we know that this is the amplitude, right? That's the number that tells you how tall the graph is above its midline. Finding the period is, well, we've done that as well. So we kind of know how to do that also. So I know it's a bit weird to have this video stop here, but just in line with having one video for each subsection of each section, I think I'll stop here and I'll make a video for the next subsection, finding equations and graphs, finding equations and graphing sinusoidal functions.